Hello everyone. In this video, we will discuss about a problem from Topology by Munkres. It is the 19th problem of the third exercise in chapter 2.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Here, they are defining boundary of a subset of a topological space. Considering a topological space X and a subset A of that, we have A closure which looks something like this, intersected with X minus A the whole closure. X minus A the whole closure looks something like this, which is outwards, because X minus A is outwards. So their intersection will be the region in between them. This is called boundary of A. So before directly jumping into the problem, we will look into some definition of limit points and properties of that. Supposing that we have closure of A, which is A bar, and that is defined as the intersection of all closed sets in X, containing A. So how we can realize this? We realize this using something called as the limit points. Suppose consider a subset A of the space X. Now, if suppose any point inside A will always be in the closure A bar, because it is contained in A, which means it is contained in all closed sets containing A. Now consider a point outside the set A, which means it is present in X but not in A. So such an element, if suppose it has an open set not intersecting A, or some basis element not intersecting A, then obviously let us call that as U containing X naught. Then X minus U is closed in X and containing A. Hence, the closure A bar will not contain the element X, because X minus U do not contain the element X naught. And we know that it is the intersection of all closed sets containing A. So this X minus U will not contain X naught, and hence A bar will not contain X naught. So we say that whichever element in X that are outside A and having open sets that intersect the set A are also the elements of A bar, because we cannot come up with a closed set that is not containing X naught and containing A. Because if we are able to come up with such a set, then there do exist an open set that is not intersecting with A but containing X naught. So hence these are called the limit points, and let us say that lim of A represents the limit points of A. Then we say that A bar is the set A, because every element of A is contained in A, and hence it is contained in all closed sets containing A. Union limit points of the set A. What are limit points? Limit points are those points whose any neighborhood will intersect the set A. So this forms the closure of set A. So using this definition, let us go to the first problem. We are supposed to show that interior of A and boundary of A are disjoint. So we are supposed to show that interior of A intersection boundary of A is null set or empty set, and that A bar is the union of interior and boundary. Now, first let us show that interior and boundary has no elements in common. Suppose if you have the space X and a subset A of that, what do we mean by interior? It is the kind of the largest open set contained in A. So formally it is defined to be the union of all open sets contained in A. Now supposing that some element y0 belongs to the interior of A. Belongs to the interior of A. Obviously interior of A is a subset of A because it is the union of open sets contained in A. Now let y0 belong to interior of A. But we know that boundary of A equals A bar intersection x minus A the whole bar. Obviously y0 belongs to A bar because it is belonging to A. But it will not belong to x minus A closure of x minus A, because x minus A is the set of elements not contained in A, and this element y0 is not in the limit point of x minus A because it is having an open set that do not intersect x minus A, and that open set is nothing but the interior of A. So y0 will not be a limit point of x minus A, and since y0 is outside the set x minus A, it should not belong to x minus A the whole bar, which imply it should not belong to the intersection of that, which is nothing but the boundary of A. Now similarly, going the other way around, suppose that an element y0 belong to boundary of A, which means y0 must be present in x minus A closure. And from here we can say that y0 should not belong to interior of A, because if it were belonging to interior of A, you will get the contradiction that it cannot be in x minus A closure. So hence, in order to avoid the contradiction, y0 should not be in the interior of A, and hence boundary of A and interior of A must be disjoint. Now we will prove the second part. A bar is the union of interior and boundary. For this, let us take the definition of boundary itself. Interior of A union boundary of A can be written as A bar intersection x minus A bar. Now we can take the union inside, and we get that interior of A union A bar intersection interior of A union x minus A the whole bar. Now interior of A is a subset of A, and which is a subset of A bar obviously. So we see that union interior of A is a subset of A bar, and hence their union is nothing but A bar intersection interior of A union x minus A bar. So this is an interesting thing to analyze. In a topological space X, if you consider the elements that are not in x minus A bar, then it must have an open set that is not intersecting x minus A, which means it is not going outside of A, which means it is completely inside A. Suppose if you take an element Z0, then Z0 belongs to an open set, or it has a neighborhood U, which is a subset of A, and that clearly states that Z0 belong to the set interior set of A, because interior is defined to be the union of open sets contained in A. So hence, if an element is not in x minus A bar, then it must be in interior of A bar. Hence we claim that the union is nothing but X, because all elements must be covered. Suppose if an element is not covered, then it is not present in x minus A bar, which means it must be present in interior of A bar, interior of A, and this states that it is A bar. So hence we have proved that interior of A union boundary of A is nothing but A bar. Coming to the second part of the question, boundary of A is an empty set if and only if A is both open and closed. Let us try to prove this. Boundary of A is phi if and only if A is both open and closed. This is easy to realize if you take A and x minus A separately. Remember, suppose we will prove the forward direction. Assuming that the boundary A is empty set, we will prove that A is both open and closed. How will I prove that it is first open? We know that boundary of A is A bar intersection x minus A bar, and we know that that is empty. From here I can say two things. A bar must be A and x minus A bar must be x minus A. Why? Because if A bar consists some elements out of the set A, then it must be present in, suppose A bar consists of element not in the set A, then it must be present in x minus A by definition of x minus A. And if it is present in x minus A, it is also present in x minus A bar. And by hypothesis, it is also present in A bar. Hence, it must be present in the intersection. But we know that intersection is empty. So there is no element outside of A. Hence, A bar is equal to A. Obviously, all elements of A must be present in the A closure. And a similar argument works for x minus A closure. If an element is not present in x minus A and belongs to x minus A closure, then it must belong to also A closure, which means it must belong to their intersection and a contradiction. You will easily see that this is true. Now, if this is true, when will A bar be equal to A? So this implies that A is closed. And this implies that x minus A is closed. Why? Because there are no limit points outside the set. That clearly means that A is closed. Typically, because if you take any element outside A, it has an open set that is not intersecting with A, which means it is completely present in x minus A, which means x minus A is open, and that means A is closed. And a similar argument for x minus A. And this states that x minus A is closed imply A is open in X. And these are if and only if statement. So you can go in both directions. And this is also like an if and only if statement. If A is both open and closed, we say that boundary of A, we will get that boundary of A to be empty set. Now let us go to the C part. Show that U is open if and only if boundary of U is U bar minus U. We will show that U is open if and only if boundary of U equals U bar minus U. Suppose we will take the forward proof. And in the space X, you have the subset U, which is also open. Now we know that boundary of U is defined to be U bar intersection X minus U bar. And since U is open, we know that X minus U is closed. And that implies X minus U is nothing but X minus U bar is nothing but X minus U. And take the intersection inside, you will get U bar intersection X minus U bar intersection. I know that U bar intersection X is U bar and U bar intersection U is U, because U bar is U is a subset of U bar. Let us try to prove the other way around. Assuming that the boundary of U is U bar minus U. Supposing that U bar looks like this. Obviously U is a subset of U bar, and boundary is U bar minus U. So boundary looks something like this. Why should then U be open? We know that if U bar intersection X minus U, the whole X minus U bar is the intersection of two closed sets, hence boundary is always closed. And we also know that if an element belongs to U bar, say X naught, suppose say that X naught belong to U, then I know that there is an open set. I know that since it do not belong to the boundary, there is an open set that do not intersect with X minus U. Because let us erase this. I know that from the definition of boundary, X naught do not belong to boundary of U. And that implies X naught should not belong to X minus U bar. That means there is an open set that is not intersecting X minus U and containing X naught, which means there is an open set, let's say V, that is containing x0 and is a subset of U. Because if there is an element not in U, it must be present in x minus U. But we know that the open set V do not intersect x minus U. So it must be a subset of U. And this is true for any element x0 of U. And that implies U is open. Because there is a basis element containing each and every element of a set and completely present inside the set is the definition of an open set. And this completes the proof for C part. Coming to D part, it is an interesting question. If U is open, is it true that U equal to interior of U bar? Suppose say that U is open. Is it true that U equals interior of U bar? Because we know that boundary of U is U bar minus U. So is it true that interior of U bar is U bar, interior of U bar, is it just U then? We will not be able to say this because suppose take a 2D plane. Consider these open sets. Say these are your x-axis and y-axis. Like consider this as an R cross R space. And consider this open set. The entire first quadrant except the line, except this axis, and consider the fourth quadrant. We know that it is open because open in normal topology, usual topology. Because if you take any element, I can always find a open rectangle that is completely present inside the region. Now, let us call this set to be subset to be A, and the set R cross R is the topological space. Now what is A bar? A bar will be the set A union limit points of A. And the limit points of A are nothing but these boundary, these points which are present in the boundary. Let us consider this to be U instead. U bar equals U union limit points of U. And hence, what will the interior of U bar look like? Interior of U bar look like? We know that U is open. And we also know that U bar will be the positive x-axis, positive y-axis, and the negative y-axis. But the question is, what will be the interior of U bar? Won't it just be the entire first and second quadrant and the positive x-axis? And is it equal to U? No. Right? Think about this. We will soon discuss the next question. Thank you.
Cheenta programs are designed for students who are passionate about mathematics. And they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.